Hello everyone. Now we are going to start new topic, sliding mode control. In this topic, we'll start with the main concept of this approach, how we can design the nonlinear control for any nonlinear system. So before we proceed to the main mathematical design concept, first let me come up the some definition, which will be very important for understanding the why you have to consider sliding mode control for control synthesis for any practical control problem. There will always be discrepancy between actual plant and its mathematical model used for the controller design. These discrepancies arise from unknown external disturbance plant parameters and unmodeled dynamics. Now, designing effective control laws in the presence of these disturbances or uncertainties is a very challenging task for control engineers. This led to a development of robust control method, and one such method is sliding mode control technique. So here, the sliding mode control is the robust control technique. So when the system is not properly known due to the unknown external disturbance, plant parameters, and unmodeled dynamics. So how we can come up with effective control which will provide the robust control algorithm or law. So now we'll take a simple example and we'll try to understand how we can design sliding mode control effectively for a nonlinear system. So first, let us understand let's take a nonlinear system. So let us let us understand the sliding mode control through the following example. So we have the system, for example, second order system, x double dot equal to f plus u. So here f is the unknown parameters. No, this is the system parameters function, and u is the control. So here we can assume this f can be disturbance or some unknown forces acting on the system, and u is the control into the system. So we can come up with this kind of system in our daily life. So now we can write in state space. If we let us define this equation number one. If we write in state space equation one, we have x1 dot equal to x2 and x2 dot equal to f plus u. So this is two equation, and here x1 we can assume as, let us assume this is the position of a particle, and x2 is the velocity. Let's assume, and here f is disturbance, or unknown forces. Okay, so also let us assume here this f is bounded. So it is the norm is bounded. Also, f is assumed to be bounded. So it means f less than some value which is greater than 0, some norm of the function f. So our control objective. So in this example, we are going to devote 2 lectures how we can design sliding mode control for this particular system. If you can understand this concept, the mathematical design concept for this equation number one, the same concept can be applied for the other dynamical system. So here, our control objective is design control law, which is U, such that it drives x1 and x2 to origin asymptotically. That is, we can write limit t tends to infinity, x1, x2 goes to 0. So this is our mission objective, and we'll fulfill this design objective using sliding mode control. But to achieve this, this asymptotic convergence of x1, x2 is a challenging problem. And so we can simply state, if you want to design simple state feedback control, we can do it, right? In the absence of this nonlinear function f. So if you consider, if you simply use state feedback control, in the absence of f, which is unknown function, we can easily derive the control algorithm for this system defined by equation 2. So in the absence of this f, equation 2 can be written as x1 dot equal to x2 and x2 dot equal to u for this case, right? And if you consider state feedback control, u equal to minus k1 x1 minus k2 x2, where k1 and k2 are positive gain, then our this system yields to be x1 dot equal to x2 and x2 dot equal to minus k1 x1 minus k2 x2. So this is basically closed loop system. This concept already you have covered while in the modern control closed loop system. And if you plot, if you do the MATLAB plot for this particular system, for the initial condition, for example, x1 0 equal to 1 and x2 0 equal to minus 2, and if you consider k1 equal to 3 and k2 equal to 4, the MATLAB simulation result we can obtain. So this is, so we'll have the result something like this. Something like this, right? It is, maybe this is, for example, minus 2, 1, and this is 0. So this is basically x1 and x2. So this is basically x1, this is x2. And so this result we obtain when f equal to 0. So we can do it in similar. You can try this MATLAB code yourself. This is a very easy MATLAB code, how to do this. Now, you can see that asymptotic convergence achieved for this particular case. So here basically we can say that asymptotic convergence is achieved for x1 and x2. Now, how to tackle this system once we have this unknown function f? Because in this, for this MATLAB code, we have not considered f in the system, the nonlinear function. Now we'll consider the nonlinear function and we'll see the result again. So now let us say when f equal to sine of t. For example, this is the nonlinear function. Sine of t is a nonlinear function, and we are going to consider this function in the system. So let's assume this is the disturbance as a disturbance. For the same initial conditions, and control gain, we have the simulation results. So this is a result. So the previous code also we can design using this MATLAB code. So if you consider here, we have considered f here. In this particular case, you have considered f, but if you don't consider f, we'll get result something like this. Something like this. So when you're considering f in our system, and if you use state feedback control, our system response are not asymptotic convergence. So it is fluctuating over time. So we have the oscillations in the system response. Now, let's assume this is the upper bound of this oscillation defined by omega. Let's assume. So here we can say, we can write here some notes for f not equal to 0, the linear feedback, because here we are using linear feedback. If you notice here, we are using linear feedback control, what you have done in the modern control. So if you use linear control for f not equal to 0, because we have taken f equal to sine of t, the linear feedback laws only drive the states to the bounded domain. That is clear. This bounded domain by this is the bounded domain by omega k1, k2. This is, we can define like this. And for f, this is our delta, some value, some normal. Okay. So to tackle this problem, how we can come up some control synthesis, if there is a bounded disturbance, how we can get asymptotic convergence of the system states. This is the main motivation having sliding mode control. So how we can tackle these issues? So in the presence of this bounded disturbance, how we can tackle this problem? So we'll go step by step to solve these issues. So let us consider, or we can write a good candidate would be homogeneous linear state, or we can write linear time invariant differential equation. We are choosing some system, linear system, which is time invariant, using the state variable x1 and x2. So here we are choosing some equation x1 dot plus k x1 equal to 0, k which is greater than 0. And from this, we can write x1 dot equal to minus k x1. So this is the homogeneous linear time variable function we're assuming. And our main motivation is how we can drive our states to follow this trajectory. This is the main motivation of sliding mode control in this lecture. So now, if you get the solution of this, let us define this equation number 3. The solution of equation 3 would be x1 t equal to x1 naught e to the minus kt. And since x2 equal to x1 dot, So we can write x2 equal to, we can write x naught. You can take the time derivative of this equation, So you can write it x naught e to the power minus kt minus k, or we can write minus k x1 naught e to the power minus kt. Okay, so we can notice that both x1 of t and x2 of t converge to 0 asymptotically. So from this we can write both x1 and x2 converge to 0 asymptotically. Okay. Also, we can notice if you have the system, this homogeneous linear time linear system, if you have system like this, so there is no effect of disturbance also in this equation 3, right? So we can achieve this by introducing a new variable in the state space of the system of equation 1. So what we're going to do is, we are introducing a new variable. Let us introduce a new variable in the form s equal to s x1 x2 equal to x2 plus k x1. So this is very, very important, which is k greater than 0. So based on this, we are defining this s variable, which can be defined by x2 plus kx1. So here our motivation is, or we can write, to achieve limit t tends to infinity, x1 x2 equal to 0 with given convergence rate, or convergence rate is, this is our convergence rate for x1, this, and x2, this, right? Convergence rate, we can write here in bracket e to the minus kt in the presence of bounded disturbance f. We have to, let us define this equation 4. We have to drive the variable as in equation 4 to 0 in finite time by the control u. So we can say that if s goes to 0 in finite time, then also we can say x1 x2 also going to evolves over time in a finite time, right? So this can be achieved, this part can be achieved if you have the Lyapunov function. We have to choose a Lyapunov function, right? Lyapunov stability condition. So now, if you take time derivative of equation 4, we can write s dot equal to x2 dot plus k x1 dot. In place of x2 dot, we can write f plus u, our original system, plus k x1 dot. In place of x1 dot, we can write x2. Right. This is equation 5. So our main motivation is we have to define the Lyapunov function in terms of S. If the Lyapunov function is negative definite, and if we can come up some structure, what we'll be doing now, then we can comment that x1 and x2 also will be stable if S is stable, right? So now we'll define, basically we are transforming the x1, x2 domain to S domain. We are transforming the variable into defined domain in S domain. So now introducing the Lyapunov function P in terms of S, we can write V equal to half S square. So we are defining the Lyapunov function in terms of S variables. So as for the asymptotic condition, we know that to provide asymptotic stability of equation 5 about the equilibrium point, which is S equal to 0. Because if you notice here, we have this is equal to 0, right? So here, and we have denoted this equal to S. So also the equilibrium point of this equation also 0. So we can write is following conditions must be satisfied, which are basically, first condition is v dot less than 0 for s not equal to 0, and second condition, limit s mod s goes to infinity and v also goes to infinity. This is already we have done while studying of Lyapunov stability theorem. From second condition, it is clear t tends to infinity, which makes t tends to infinity, right? And for this is the first, this is the second condition you're getting, and for to achieve finite time convergence, condition 1, which is this condition can be modified as v dot less than equal to lambda v half, where lambda is greater than 0. So if you can write this v dot in this kind of structure, then we can say system will be finite time convergence. And if you integrate this equation, let us define this, the equation number 6, separating variables and integrating equation 6 over time over time 0 to t, we get v half t less than equal to minus half lambda t plus v half naught. So this is equation number 7. If you integrate this equation 6, you will get the expression. Now, from 7, Vt reaches 0 in finite time. Tr, and which is bounded by this Tr is bounded by Tr equal to less than, we can write 2 to v half naught divided by lambda. So this is the expression finite time convergence of the states. This is very, very important solution. And now we'll prove the finite time convergence of this control. We can write here, hence control input, which is basically u, it will be designing now, is computed to satisfy equation 6, which is defined by this. So basically we have to design, so the main part is we have to design in this expression u here, u, such that v dot will be in this form. So once you have this form, we can get the finite time convergence expression like this, TR. This is the main motivation having this mathematical formulations. So now satisfy 6, which will drive variables is to 0 in finite time, and stays there forever. So now we'll apply. So this is our Lyapunov function, this expression. Okay, so let us define. Stop. So taking time derivative. So these are the parts, these are the stops to satisfy these conditions. Now we are going to move to our main problem, which is defined by star, the Lyapunov function, which is defined by s, and s is also function of x1 and x2, right? Now taking time derivative, of v in equation star, we have v dot equal to s dot, and s dot we can substitute our this expression, right? So we can write f plus u plus k x2. So now let's assuming u equal to minus kx2 plus v, we are assuming, and where v we are assuming as some signum function v equal to minus rho signum function is where rho is greater than 0. The signum we can write sometime SGN is we can write plus 1 if ST is greater than 0, minus 1 if ST less than 0, and 0 if ST equal to 0. So this is, let us define equation. Okay, this is equation 9 and this is 10. Okay. So now we can write, if you substitute this u in equation 9, we can write substituting u in equation 9, we can write p dot equal to is a plus b, and we can write sf plus sp. And this is also we can write in bounded disturbance form. We can write p dot less than equal to s delta plus sp. This also can write because already you have taken the bounded value of f is delta, and let us define this is equation number 11. Now, in this expression, if you substitute the value of v in 11, so we can write now substituting v equal to minus rho sine s in equation 11, we can write v dot less than equal to s delta plus s minus rho sgn is, we can write, and from this, so here we can write so s into sgn is also we can write mod s, right? Because always it is positive, we can write mod s. So we can write from this delta minus s rho, right? Or we can write s delta minus p. This you also can write. And let us define this equation number 12. Now, also already we have this expression here, equation 6, already we have this structure, v dot equal to, you can write for the finite time convergence. This is the expression we have for the standard sum for this standard conditions. So this is the one we have obtained for the finite time convergence for any s, right? You can write also we have from equation 6, from equation 6 we have v dot less than equal to lambda v half, which is equal to, we have lambda root 2 s. We can write in this form since v equal to 1 upon s square. This also can write. So now we can compare equation 12 and equation 13. Now comparing equation 12 and 13, we get v dot, we can write minus s rho minus delta equal to minus lambda root 2 s. Or we can write rho equal to delta plus lambda by root 2. This you also can get from this above equation. And let us define this equation number 14. Okay. And so we have the row now. So the control, we can now substitute this V, our control algorithm U here. We can substitute this V in control U here. Just so we can substitute here like this. So the overall control, hence the total control is U of t equal to minus kx2 minus rho SGN S. This is 15. So now this is the sliding mode control algorithm for the system defined in equation 1. This equation 1. So this is how we can design the sliding mode control. But as you proceed slowly, we'll understand more stuff in this concept. While we'll be taking the practical problems, we can come up with a better picture how easily can design sliding mode control. So now in this U of t, this U of t can be represented as here U of t can be represented as U of t equal to U EQ t plus U SW t. So here U EQ t is called, it is basically compensates the known dynamics, and USWT ensures robustness against disturbance and finite time convergence. And this EQ is called equivalent control, and this is called sliding control. So we can write from this equation, EQ is minus kx2 and USW minus rho SCNT, SGNS. So this is our overall control, sliding mode control for the dynamics one. We are actually understanding the problem, but as we proceed other examples, it will be easy to design sliding mode control, because we will be following some proper setup how we can come up the sliding mode control for the nonlinear system. In the next lecture, we'll be doing more observations. What are the different scenario happening in sliding mode control book? Because those are the parts it is required to understand more on sliding mode control. Because if you notice here in the control, we have this function, and this is basically, if you notice, SGN of S, it will give -1 or +1 or 0. So due to this, we have in the control, we have some chattering. So how to tackle all these issues, we'll be discussing in detail in the next lecture. Thank you.